I hope that I have begun to convince you that it's the actual delta G and not the tabulated biological standard state delta G that actually is important to determining within a biological system the overall favorability of a reaction. But the hard thing is that we can't always know the actual delta G, and that we wouldn't be able to tabulate that because it may change within a particular biological system. So here's an example that I'm hoping will help you, and we're going to come back to this example. This is a reaction that those of us who spend a little time in the weight room are familiar with. This is phosphocreatine. Phosphocreatine is a high energy phosphagen that can be used to power the synthesis of ATP. However, strength training, those who do strength training, sometimes, I've never done this, but sometimes people will supplement with creatine. And creatine supplementation will change the concentration of free creatine, which will then change the likelihood of making phosphocreatine to then be tapped into in times of need to power the synthesis of ATP. So what I hope to convince you of with this quick example is that it actually is the concentration of products and reactants that determine what the actual delta G is and how it will relate to the tabulated standard biological state delta G. Let's look at the math a little more to further convince ourselves that it's all about concentrations of products and reactants, maybe whether you supplement your diet with creatine or not, as to how the actual delta G will relate to the biological standard state delta G.
So here's an equation that relates the two, the actual delta G with the biological standard state delta G, and we see that the other variable here is a collective term, RT, natural log of the products of the reaction divided by the concentrations of the reactants. So products over reactants. This is something that looks probably familiar to you guys, but now let's notice that what this means is that in order to calculate the actual delta G as a function of the biological standard state delta G, we have to know something about the concentrations of the products and the concentrations of the reactants. Sometimes that is known and sometimes it's not. In fact, sometimes it's difficult to determine within the cell what the actual exact concentrations of products and reactants are. However, sometimes that is very possible, and we can compare then, likewise, the actual delta G with the biological standard state delta G, recognizing of course that R is the gas constant, which some of you will recognize as 8.315 joules per Kelvin mole. Now, we're going to come back to this idea of relating actual delta G and biological standard state delta G after introducing another term, and one that you will recognize, and showing how it relates to the standard state delta G. So let's introduce this term by looking at a situation in which we would be at equilibrium. So in equilibrium conditions, the actual delta G is going to be equal to 0. Now, just to make sure that everybody understands that, we're going to go ahead and write this down. The free energy change is equal to the free energy of formation for the products minus that of the reactants. At equilibrium, the rates of forward and reverse reactions are the same. So we would say then this overall delta G would be equal to 0. These terms would be equivalent. Okay, so that's why we can make sure to go ahead and insert for delta G that value of 0. Let's go ahead and do that and see where our equation takes us. So inserting a 0 there, we then get delta G plus RT, the natural log of products over reactants, and we can just go ahead and subtract delta G naught prime from both sides of the equation and get this equation that biological standard state free energy change is negative RT natural log of products over reactants. Now, this value right here, products over reactants, does that remind you of a constant Indeed, it is the equilibrium constant. So the KEQ, a familiar value I think to most of you, products over reactants. And let's go ahead and insert then at equilibrium conditions this term KEQ. So the natural log of that constant. This is an equation, if you will, of somewhat of importance because it does give the delta G, or the free energy change, as a function of the equilibrium constant. So this equation right here is one that is valuable and can be used to relate those two terms. Let's manipulate this equation just a little bit so that we can better see the effect that the equilibrium constant has on the free energy change, and likewise. Okay, let's go ahead and just convert natural log to a base 10 log, and that's the next step here. So a simple conversion of natural logs to base 10 logs, and then we can simply take the log of both sides of the equation, or the inverse log of both sides of the equation, and we get KEQ is equal to 10 raised to the negative delta G naught prime divided by 2.303 RT. Now the purpose of the conversion is that sometimes it's just useful, right? Because maybe you'd rather calculate KEQ, or maybe sometimes you'd rather calculate free energy change, so manipulating the equation in that way is really valuable. But also manipulating the equation in that way better shows us how the free energy change relates to the equilibrium constant. And in fact, let's think this through, because we just talked about the idea that a negative delta G is a spontaneous reaction. So if we look at how that relates to the equation, if this value is negative for the delta G naught prime, negative times a negative is a positive, so the KEQ is greater than 1. Okay, so this is important. Let me convince you of this. So a delta G naught prime that is negative, meaning that the equilibrium lies with products, right, is further reflected in an equilibrium constant that is greater than 1. So when we draw that free energy as a function of reaction progress, we see in two ways here that a free energy change that is overall spontaneous, overall negative, also of course relates to an equilibrium constant that is greater than 1, meaning that the equilibrium lies with products. Cool. Now, likewise, we could say the same thing if we had a delta G naught prime that was positive, then this term, KEQ, 10 to the negative number, would be less than 1. So KEQ less than 1 lies with reactants, and we would see a swapping in the curve, right, where the reactants were actually at a lower energy state than the products, and the delta G naught prime is then a positive value. Excellent. Now, one more thing. If this delta G naught prime is 0, the KEQ is 1. So KEQ equals 1, where delta G naught prime is 0. So the two really do relate to one another, and by knowing the equilibrium constant, we can also calculate the delta G, or vice versa. This is a fantastic equation, and one that I guarantee you will see again. Before we leave this behind, I do want to note something else about the magnitude, or the order of magnitude of the change. If KEQ changes by, or if, let's do it this way, if delta G changes by just a tiny bit, for example, if delta G naught prime doubles, say it goes from 5.7 to 11.4 kilojoules per mole, KEQ is going to decrease by a factor of 10. So just tiny changes in the overall delta G naught prime will lead to very large changes in the equilibrium constant. So in terms of order of magnitude, let's write that down. I'm sure you're all getting a little bit anxious by now because you're like, okay, good enough, Rachel. We know how equilibrium constant relates to the standard free energy change at standard biological state. But what we want to know is we want to know how is it that you determine the actual free energy change as a function of the biological standard state free energy change. And if we know the concentrations of products and reactants, then that's something that we can do and can relate. So we recognize that when delta G is equal to 0, the equilibrium constant describes that ratio. Okay, so we can just use the known KEQ to describe that ratio. But not always are we at equilibrium. Not always is the actual delta G equal to 0. So if it is not, then this ratio of products over reactants is not the equilibrium constant. What do we call it and how do we use it? So if we're not at equilibrium, then the value of delta G actual still depends upon the concentrations of products over or does depend upon the concentration of products over reactants, and that value we know will not be described by KEQ, and so it is given a special name called the mass action ratio. And in fact, it is that mass action ratio that determines how delta G and delta G naught prime relate to one another. So we could in fact plug in this value Q to describe the concentration of products over reactants. And in fact, as we've said so many times, and you're getting tired of me saying, it is this value of actual delta G that tells us the reaction spontaneity as opposed to the free energy standard biological state delta G that we have here. And of course, the thing that relates the two is this mass action ratio. So let's write this down. Delta G and not delta G naught prime is the criterion for assessing reaction spontaneity. Star, 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 right? This is very important because it is in fact the case that the actual delta G is the real criterion for reaction spontaneity. Even without plugging in numbers, it is very easy for us to see the relationship between the actual delta G and the mass action ratio. It all has to do with the ratio of products to reactants. Remember that that's what describes Q. So if we have a situation where the concentration of products is greater than the concentration of the product of the reactants, then we have a scenario where Q is greater than 1. The natural log of a number greater than 1 is going to be a positive number. So under circumstances where C times D is greater than A times B, then we will see that this number is positive. So if the value of delta G naught prime is a negative number, then the reaction, the actual delta G, will be more positive, that is less spontaneous. Now if the opposite situation is considered, a situation in which the concentration of reactants, A times B, is greater than the concentration of the product of the products, then we get a situation where Q is actually less than 1. In that scenario, our sign changes here. The natural log of something less than 1 is going to be a negative value. Thus, we see that in this situation, the actual delta G would be more negative than was the delta G naught prime. So the actual delta G would show that this reaction would be more spontaneous than predicted by the delta G naught prime. So everything comes down to having to do with Q, doesn't it? Because if you have a ratio here that is greater than 1, then it makes this value more positive. If you have a ratio as less than 1, it makes that value more negative. So we see how Q relates to the actual delta G. We can bring ourselves to the big take-home message. And that is the idea that this mass action ratio, and really the term kind of gives this away, right? But what we can say is that the relationship between Q and KEQ, the mass action ratio as versus the equilibrium constant, tells us whether or not the reaction is near equilibrium or whether it is metabolically irreversible. So if Q, this value, is very close to KEQ, then it makes sense to say that the reaction is very close to equilibrium, so we have a near equilibrium reaction. On the other hand, if Q differs a great deal from KEQ, we know that we are very far from equilibrium and that we have a reaction that we would term metabolically irreversible. So how do you know? How do you know how much variance is between Q and KEQ is relevant? How do we know whether we assign a reaction as being near equilibrium or whether we call the reaction metabolically irreversible? Well, the rule of thumb is that if the Q differs from the KEQ by 2 or more orders of magnitude, then we call the reaction metabolically irreversible. So what does orders of magnitude mean? That might be an important thing to note. Orders of magnitude just means factors of 10. So if Q differs from KEQ by 2 or more factors of 10, then the reaction is said to be metabolically irreversible.